Today we want to look at functions of two variables. This is going to be our starting point. If you recall, last time we mentioned that a function of one variable produces a one-dimensional curve in two-dimensional space. When we increase to two inputs, but one output, we'll end up with a two-dimensional surface in three-dimensional space. And then this will keep on going. If we have a function of three variables, we'll have a three-dimensional solid in four-dimensional space. If we have a function of four variables, we'll have a four-dimensional solid in five-dimensional space. These are the ones that we kind of need to get through, because this kind of covers everything. Here, at least the slices look like three-dimensional things that we can picture. Going one more, we're in R5 and we're thinking about four-dimensional things. Now it's harder to draw pictures. We do the same kind of thing when we talk about distance is equal to rate times time. Velocity is the derivative of position, and acceleration is the derivative of velocity. We can have a derivative of acceleration. We call it a jerk, but we don't see it very often. So we just kind of stick to those first two. I know I said two, but there's like position, and we have two derivatives that we care about. So I suppose that we could say that the position is the 0th derivative of the position. But that would be strange. So this 1, 2, and 3, depending on the inputs, that's how much space we're taking up with the inputs and how much space we're leaving for the outputs. The limitation here is that we're dealing with a function. That's a limiting factor. But this is a good starting point for dealing with things in surfaces in three dimensions. So the limitation is that one function should be more specific. One variable is a function of the other variables. Requiring that we have a function for a structure is a big limitation on what we can do. But this is a good starting point. Like when you start off in physics, you ignore air resistance and you ignore friction. Just make sure your stuff isn't going too fast, and air resistance is not going to be a big deal anyway. But the reason for that is, even though air resistance is a thing, we want to ignore it at the beginning to simplify our calculations because we're new. So when you first start studying physics, you don't want to put everything in there. You just start with what's necessary and ignore the things that will just complicate matters, especially when you're planning on complicating those matters later on anyway. So it's very limiting to require that we have a function of two variables, but it's useful for our purposes. Any questions? Here's what oh, go ahead. It depends. So pretty much every answer it's going to be like on legal. It depends. It depends. It depends on what those four variables are going to represent. So it could be that our four inputs are just location and time. Maybe our function of four variables has three spatial variables, meters, 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 and then the fourth one is just seconds. So we're watching something change through time. It could be that we're watching a surface morph through time. So I have a meters, and then the third one is seconds. It could be that our third input is seconds. and then we're measuring something change over there. So it all depends on what we want to measure. That I have to leave to the physicists. They can deal with that stuff. We're just going to work out the math parts. Good question, though. Why do we care about things that are bigger than R4? At this point in your mathematical careers, it's kind of because we can. A lot of times in early math classes, and you're still in an early math class, I know this feels like super advanced because this is the farthest you've ever gone. 50 years old feels super old because this is the farthest I've ever gone, 50 something. So a lot of times in our early math classes, like, oh, dude, when am I ever going to need this? And my answer is, the best answer is, I don't know. I don't know what you're going to be doing in 5 years. I'm not allowed to look into the future and see what happens. I'm not allowed, I don't know. A lot of you here in class now, in your presumably second of 4 years of college, are going to be doing a job in 10 years that doesn't even exist right now. So if I prepare you for jobs that are out there, are you going to be prepared for the job that doesn't exist? That's the big question. Does that make sense? So let's talk about this limitation of having a function. Let's bring it down to a space that we are familiar with. And see why this is, see how limiting this is, just as one example. Because it's Monday and because it's 8 o'clock in the morning class, I have to use this. And it is like the most basic. I mean, this is teacher so basic. So I'm just going to use this one. And I'm even going to have a fixed value for the radius. When we look at the equation x squared plus y squared is equal to 9, we know that this produces a circle with a radius of 3 centered at the origin. Here we have a circle of radius 3 centered at the origin. That's the set of solutions to this equation. So this equation is defining a relation between the variables x and y. But I cannot write a function here that describes that circle. Not one function. We can see that we each x, or not each x, but many x's correspond to 2 different y values. So we cannot write y as a function of x. So y is not one function of x. Each x correspond, or some x correspond to 2 different y. Some x correspond to 2y. That means we cannot write y as a function of x. We can write y as two separate functions of x, but we need two functions. So I can say that y equals the square root of 9 minus x squared. But in writing this function, we undid a square. The problem with undoing squares is that the square function isn't one-to-one. I can't just undo a square. It gives us two values. A positive and a negative. Even exponents do not respect negatives. They just try to make everything positive. All of us have an even exponent somewhere in our life. We show up, we're feeling kind of sad on a particular day, and they're like, "Oh, cheer up." We're working under the assumption that being happy is the required default state, and it is not. And that's not how that works anyway. You can't be like all sad and someone be like, "Oh, cheer up," and you're like, "Oh, whoo, thanks." Same kind of thing when someone's really angry. And someone's like, "Oh, well, just calm down." Like, "Oh, whoo, thanks. I was really pissed right there, but telling me to calm down, that really fixed everything." I mean, that's just not how emotions work. But anyway, moreover, x is not a function of y. Because some y correspond to 2x. We can write x as two functions of y in the same way we did for y. So we can say that x is positive square roots of 9 minus x squared, and I said x. Minor John Malkovich moment here. X is equal to 9 minus y squared, or we can write x equals minus the square roots of 9 minus y squared. So we can express x as two different functions of y. Each corresponding to half of the circle. This particular structure is going to be important to us later on when we're starting to build out a library of surfaces that we can recognize. So let's take a moment and see this y equals square root of 9 minus x squared. That represents the top half of the circle. So that represents the top. The negative square root represents the bottom. That makes sense. The top part is the part that's not negative. And the square root of something is not going to be negative. So if I multiply that square root by a -1, it is not going to be positive. Similarly, down with the x equals plus and minus square root of 9 minus y squared, we have half of a circle. We get a semicircle. In x equals positive square root of 9 minus y squared, we're looking at where x is positive. So that'll be the right half of the circle. And then when x equals negative square roots, we're looking at the left half of the circle. So here we have a very important relation between x and y that we can't express as a function. We are still going to start talking about multivariable calculus with functions, and also specifically of two variables. How's everybody okay? Incorrect. It's Monday, 8 o'clock, and we're in a math class. This makes maximum meh. It might be like, oh, meh. Eh. That's the important scale. More importantly, can we cope? That's the only one to really cope. How's everybody okay? See, that's a follow-up, like just the previous one. It's like, oh, you just told us that we're not supposed to be okay. I'm just trying to determine exactly how much control I have over your state of mind. Because this whole game is all about manipulation, right? I'm just trying to manipulate you to do the things that I want. It's really frustrating because the main way we manipulate people is by giving them money. And yet, I'm not giving you any money. In fact, I'm giving you negative money. So I guess it's just negative money. And it's not me personally. Back off. It's not me that took your money. You chose to do this. My whole plan is to like pay you. I want to motivate you properly in the American way. I want students to be your job. I want you to show up, clock in the morning, take your classes, and then clock out. That way you don't have to go to some other job that's distracting you from this one. I realize that your work in this class is going to come in second to some person out there that's giving you money for your time. You know what I mean? Anyway. What are we talking about? Oh, yeah. So we're going to limit ourselves by dealing with functions. Let's take this and do the Calc 3 thing to it. Right now, this is something familiar. We can break it down into functions, and it's in R2. It's just a one-dimensional curve sitting in two-dimensional space. It's one-dimensional, even though that we need 2 dimensions to draw the thing. It's one-dimensional because if you're on the curve and you're locked onto the curve, you've got 2 choices. Left, is that left? I'm looking at the other side. I'm looking from behind the screen. So you've got left and negative left. Those are your only 2 choices. One is -1 times the other. So you really don't have 2 choices. You just multiply by whatever scalar you want. So that's why I'm describing this as a one-dimensional thing, just stuff on this piece. Let's take this up 1 dimension. Let's go from a relation between 2 variables to a relation between 3 variables. A relation among 3 variables, is that the right word? How about just with? I think it should count in a spelling contest if you bail on the word and spell a synonym. I think that 100% should count. So I'm going to go to a relation from a relation with x and y to a relation with x, y, and z. We are describing a relation among three variables. Here we have a relation among three variables. When we had two variables, we ended up with a circle. This x squared plus y squared equals 9. That was a circle. If I have three variables, what's a three-dimensional circle? A sphere. We've just gone up one, so this is a sphere. A sphere with a radius of 3 centered at the origin. In this case, we want to see this x squared plus y squared plus z squared. This is everything that is exactly 3 units away from the origin. It all comes from the distance formula. The same way we had with x squared plus y squared equals 9. Everything exactly 3 units away from the origin. We can discover this with the distance formula. So you don't have to take my word for it. In this case, I can't write one variable as a function of the others for the same reasons same problems that we had with the circle. We still can't write one variable as a function of the others. For the same reasons that we have with the circle. But that doesn't mean that solving for one of the variables doesn't produce something useful. You can tell I was not practicing writing circles over the summer break. This one's a little too squashed in, and I clearly overcompensated on this one, so it's all bulging out, but that's all right. This is math class, not art class, so if I say it's a sphere, it's a sphere. The traditional way to label three axes when you're writing in 2 dimensions like we are here is to try to describe the x and y as like the floor and the z as being the vertical. This is not necessary, but this is typical. In the same way, it's typical to write our x coordinate horizontally with positive to the right and y vertically with positive to the up. This is why gravity is negative 9.8 meters per second per second. So to give it this kind of some depth, we draw a waistline on our little circle. That makes it look like a sphere. We can imagine taking this circle in the YZ plane and spinning it around the y-axis, and that's going to produce a circle. Notice that we have 3 dimensions. Before we only had 2. We had top and bottom, and we had left and right, but now we've got three. We've still got top and bottom. We've still got left and right. I'm going to relative to where we're standing here, a little bit off the positive x-axis. But now we have a third one. We have front and back. So in this arrangement, we could say that z equals positive square roots of 9 minus x squared minus y squared. And we could write z equals the negative square roots of 9 minus x squared minus y squared. We can produce these two functions. We can produce these two functions describing two halves of our sphere. The positive square root is going to be the top with the orientation that I've described here. So the positive one will be the top. And the negative one will be the bottom. Following the same kind of thinking, similarly, using this orientation that I've decided where y is going from left to right, if we solve for y, in this orientation, that will give us the left and the right. Oh, I should go positive, negative, right and left. And if we solve for x, that'll be like the front and the back. Questions? How's everybody? Okay. I told you the calculator is the easiest one. Always hard to decide what to do on a Monday morning for class. Should I just talk and everybody just write stuff down, or should I like be having some quiz or don't call it a quiz, but should I have some problem for you to all do? Because I had left the problem hanging on Friday. And you'll notice that that problem is still hanging today. When that happens, you can kind of expect that problem to show up in the discussion section. So you can score points on it that way. That one's pretty good because then otherwise, that way you're not on the spot. It's like breakout rooms. Like, oh, let's try to solve a problem. It's like, oh, no, that's not how my problem solving works. I have to go and think about it for a while I'm doing something else. I have to run it in the background. Then maybe I can come up with a solution. I don't like the thing where everybody's like, oh, let's brainstorm. It's like, oh, no, brainstorm is just going to wreck the ship. You know what I mean? For a long time, I felt kind of bad because we'd be put into groups and then be required to brainstorm. I'm like, well, I can never come up with anything during the friggin' brainstorm because it was short-circuiting my entire thought process. However, after it was over and I contributed nothing to the group or the breakout room for the modern audience, after I've contributed nothing to the breakout room, later on it's like, oh, wait, here's an idea. You know what I mean? And even better, I'm like, oh, here's why all your ideas were bad. I usually don't phrase it that way. That's just an attempt to be more professional. I said attempt. Any questions? We're trying to take the stuff that we are familiar with and adapt it to this new environment where we're looking at relations of more than one variable. And right now, we're just working on that first big piece of the three things that we do in calculus. Describe stuff. Here we are describing stuff. Then we're going to take the stuff that we describe and apply calculus thinking to it. So here is our next describe stuff activity. So contours and level curves. This is going to give us some techniques for how we can visualize higher dimensional objects in lower dimensional spaces, looking at lower dimensional spaces. So for example, imagining something that's three-dimensional on a page. This is how we can describe higher dimensional objects in lower dimensional spaces. So let's grab our sphere of radius 3 again. And we're going to look at level curves of the sphere. For a level curve, we're going to pick one of the values, one of the variables, and give it a constant value. That will drop one of our variables out. So giving one variable a constant value drops us down to a relation between two variables. So for a level curve, we're going to look at one variable and give it a constant value. This will result in a relation between two variables. And a relation between two variables we can represent in R2 with a one-dimensional curve. And then we'll just do the same thing that we always do. Pick another value, pick another constant, and see what that gives us. If we choose a value of z equals 0, that's going to give us the equation x squared plus y squared equals 9, which will be a circle of radius 3. So what we're doing is we're imagining the sphere, and we're going to look at it, look at our 3 dimensions from the top. We're going to move ourselves to the positive z-axis and look down on the sphere. And so our level curve is a circle of radius 3. So here's a level curve where z is equal to 1. You want to see where this is going next? Sorry, where z is equal to 0. I spelled 0 wrong. I also pronounced it kind of weird. Yeah. Because reading isn't my strong suit. Thank you. And I was thinking circle of radius 3. And so my arm was like, well, all right, I'll write 3. And my brain was like, oh, no, radius 3. Someone will notice. Nice catch, thank you. Sometimes I don't notice, and I scan the notes and I post them. I'm like, oh, no one caught that. Everybody loses 100 points.
I was just wondering how you could take the square root of one side and not the other.
Yeah, only by cheating. So now that that's sorted out, we can see where this is going to go next. I'm just going to pick another value of z and see what kind of level curve we get there. So if z is equal to I'm starting to remember now why I used 4 in the past, but it's okay. If z is equal to 1, then our equation looks like x squared plus y squared plus 1 squared is equal to 9. And so x squared plus y squared is equal to 8. So I have a circle with a radius square root of 8. See, I circumvented that short circuit by writing it first, then saying it. And then we just look at another value of z. So I have a circle of radius 5. So this is graphing a function a little bit differently than we do normally. Normally, we pick an input and we draw the output as some height above our inputs. But in this case, height, since we're viewing from above, height all looks the same. We can't see the lower and the higher values. So I have to let the reader know what's going on. This is the floor. This is sitting on the XY plane. This is 1 unit higher. This is 1 unit higher still. This can go on until we run out of Z values. Say when Z is equal to, oh, I didn't use dot, dot, dot. That's why I picked 3. So when Z is equal to 3, X squared plus Y squared is equal to 0. So all I get is this point up there. Any questions? How's everybody okay? Told you, Calc 3 is going to be the easiest. This is just describing stuff. How much calculus did we do today? The right amount, 0. Always do as little calculus as possible. Remember your algebra class and all that stuff where the teacher was like, "I'll show your work." It's valid to leave that blank and just write the answer if that was your work. You know what I mean? And like, I'll show all relevant calculations. And it's like, oh, I don't have any relevant calculations. I just know that x plus y squared, the square of the sum of x and y is x squared plus 2xy plus y squared. I don't need to FOIL. I don't need to write it out. Then the teacher's just like, oh, write it out. They forget sometimes that the point of the math class is to stop doing all the friggin' calculations and just arrive at the answer. The thinking is what's important, not just like writing stuff down. You know what I mean? But then we try to memorize our way through the math class, and that doesn't work either. All right, so that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.